Hello, and in today's ATmega328P tutorial, we are going to be covering the analog to digital converter. Now first, let's go over the schematic. The most important thing here on the schematic is I have a potentiometer or variable resistor connected to the ADC 5 channel on the ATmega328P, and that's just connected to VCC and then ground on the two outer pins, which creates a adjustable voltage divider on the ADC 5 pin. And then I have the FTDI connected, two switches for the interrupts, and then we have 8 LEDs connected, with 4 being on the D port and then the other 4 on the B port through here. So the D port's going to have our lower half of LEDs, and then port B is going to have our upper half of the LEDs connected. And this is just to display values from the ADC. Okay, now let's get into the datasheet. Okay, in section 23 of the datasheet, we have the analog to digital converter. The analog to digital converter is a 10-bit analog to digital converter. We have a conversion time from 65 microseconds to 260 microseconds. This is dependent on what your oscillator is. And then you can have a maximum of 15k samples per second. The ADC has 6 multiplex single-ended input channels and then 2 additional multiplex single-ended input channels. So basically just the difference between these two channels are the 6 channels can have them either as analog or digital inputs, and then the 2 other inputs are dedicated analog inputs. Then we also have an analog temperature sensor inside the ATmega328P, which has a linear scale to whatever the temperature is inside the chip. We have a optional left adjustment for the ADC readout. We'll be covering this later. And then we have a 0 to VCC ADC input range, so we can have an input from anywhere from 0 volt to the Vmax the chip is currently connected to. Then we also have a selectable 1.1 volt ADC reference voltage. Now the 1.1 volt is basically for the temperature sensor, and it can be used as a precision voltage reference if you don't want to use the supply rail as your voltage. Then we have 2 modes we can run the ADC in. We have free running and single conversion mode. The mode we are going to be setting up is single conversion mode, and we can have the ADC as a interrupt, and I have a sleep mode canceller as well. So for 10 bits, that means we have a resolution of 0 to 1023. That is our range, so we have 1024 levels. Then we have a diagram of how the ADC works. We'll come back to this diagram. Now, starting a conversion. A single conversion can be started by disabling the power reduction bit of the ADC. Now, this power reduction bit is not actually that important for here, since we are not using sleep state at this stage of the tutorials. But just be aware that bit has to be taken into account when you're using sleep states on the ATmega328P. And now here's the important one. Writing a logic 1 to ADC start conversion bit ADCS will start a conversion for you. And then we have a diagram of how it works. So basically by writing a 1 to ADCS, you just trigger this entire block. So it checks, okay, which pin am I doing? Then we check the trigger edge. Am I enabled? And then it starts the conversion. And then there's a prescaler as well, which we are going to discuss a bit later now. Okay, then we have the prescaling and conversion timing. We have a prescaler anywhere from divide by 2 all the way to divide by 128. This is controlled by the 80 bits, SO0 to SO2, and that selects what the prescaler is going to be. By default, successive approximation circuitry requires an input clock frequency of between 50 and 200 kilohertz to get maximum resolution. So if you want to get the full 10-bit resolution of your ADC, you have to be in this range for the ADC. We are running at 16 megahertz. So the simplest is going to be divide by 128 to give us a sample frequency of 16 million divided by 128, and that gives us a sample frequency of 125 kilohertz. So 125 kilohertz, which is in this range over here. And if we take it again, 16 million divided by, what's the next one, 64. You can see we go to 250 kilohertz. Now the thing is, with the 250 kilohertz resolution, you can see here if a lower resolution than 10 bits is needed, the input clock frequency of the ADC can be higher than the 200 kilohertz to get a higher sample rate. But we want the full conversion rate, so we need to stay below 200 kilohertz, which is now our 125 over here. Okay, then they have channel or references. This is basically just if you want to switch your reference and or your input. Basically, the most important bit here is once the conversion starts, the channel and reference selection is locked to ensure sufficient sampling time for the ADC. So if you switch your reference and or the channel that is currently the ADC's input, then if you have a conversion currently running, it's first going to finish that conversion, then change your values when the current conversion is done. But we are going to only run a single channel on this to avoid complexity. And then they just say here with input channels that you need to follow the above guidelines. Now we have ADC reference, the reference voltage for the ADC. ADC ref indicates the conversion range of the ADC. So your reference voltage is basically your Vmax. And then they say if you go over the voltage of the voltage reference, it's just going to top out at the maximum value, which is 3FF, which is also known as 1023. Now don't go over 5 volts on this chip because you're going to pop it. Then you have your AVVCC, which is your supply voltage as the reference. Then they have the internal 1.1 volt reference. Then you have the AREF pin, which is used to set the reference voltage externally. We are going to use AVCC, so the supply voltage. We are going to give it the noise canceller a skip because that's just a CPU feature. There they just give you an explanation of the analog input circuitry. They just give an explanation of the equivalent circuit of how it works. Then they go over analog noise cancelling techniques. Your easiest technique is just average your output voltage. We are not going to handle averaging in this tutorial. And they give a power connection. Here is the suggested for the AVCC. So they have a low pass filter from VCC with a 10 microhenry inductor and a 100 nanofarad cap. I am too goddamn lazy to do this. Here they give a bunch of information that is generalized to ADCs. Now they give the voltage conversion formula. I am not a fan of this formula, but basically you have your input voltage over here and you have your reference voltage over here. This relies on your Vin to be constant. Then they go over how the temperature sensor works, which we are not going to do in this tutorial. Then we have the register descriptions. So the first register we're going to go over is ADMux. This is the ADC multiplex selection register. Bit 7 and 6, which is the reference selection bit. So 00 is the analog's reference pin, which is the default. And then we have our AVCC for the first selection. Third selection is reserved. I'm going to assume that is for another chip. And then we have a 11, which is the internal voltage reference. We are going to use AVCC as our reference. So these two bits are going to be 0 and 1. And then we have the ADC left adjust and right adjust. You can toggle these on off. And there is a description later in the datasheet that actually shows this nicely. But for now, we are going to leave this as, I believe, 0. Right 1 to this bit for left adjust the result, and then otherwise right adjust. We are going to have it as right adjusted. Then we have reserve bits, which are unused, and then we have the analog channel selection bits. So this selects which pin your current conversion is going to select from. Now we have the table, so all the way from 0 to 7 gives us the input channels for the external pins. And then we have number 8, which is the temperature sensor, if you can see here from the note down here. And then we have a bunch of reserved ones, which is usually for another chip, like say the ATmega chips that have a lot more inputs but use the exact same CPU architecture. And then we can directly go to the 1.1 volt reference, which we can use for calibration, and then we can also go to the ground as a reference. So we can always output 1.1 volts to the ADC channel depending on the reference. Then you can use that for calibration. But in our case, we are going to hard set it to ADC 5. And then we have the ADC control register, with bit 7 being our ADC enable. So if we write a 1 to the ADC, we are going to turn the ADC on. Then we have the ADC start conversion bit. Now this bit, if we write a 1 to it, we start the conversion. Just something that might be of interest. The first conversion takes 25 ADC clock cycles, while the rest of the ADC conversion clock cycles will take 13. So typically what you would do, you'll first just do a dummy conversion and just chuck away that data so that the ADC is initialized. Then you would take your normal samples. Then we have the ADC auto trigger. We are going to disable this because this is for much more advanced ADC conversions. If you have like a precision time you have to do it or something like that based off a timer or some other event, you can trigger the ADC off it. Then we have the ADC interrupt flag. We don't use this bit. This bit is auto set and auto cleared for us when we enable the interrupt. Then we have the ADC interrupt enable. We are going to enable this interrupt. So basically just write a 1 to it so that it is active. You can see where when it's written 1, interrupt is active. Then we have the prescaler selection bit, which we handled earlier. We are going to have it as 111. So we divide the ADC input clock by 128. And then we have our data registers, which actually contains the registers we want. And here is the bit we mentioned earlier that is in the ADC mux register that shifts the register left or right. So this is right justified is when ADLAR is equals to 0. So this is how your registers are going to look. So 2 of your most significant bits is going to sit in ADCH and your least significant bits are going to sit in ADCL. So your lower ADC register. If ADLAR is equals to 1, have the register set up like as follows, with the lower 6 bits being useless in ADCL. Now this is useful if you're only using 8 bits, because then all you need to do is ADCH read and you don't need to do any bit shifting. But for full completeness, so I have full access to the resolutions, I'm going to do this and manually shift the ADC register. And something very important, because I got stuck on this when I did the example stuff, when ADCL is read, the ADC data is not updated until ADCH is read. Even though the conversion says it's done, it does not update the registers. You can keep calling and your data won't change for your ADC registers if you do not read the ADCH register. And then we have the ADC control and status registers B. These are information bits. We are not going to use the ADC auto trigger sources. For some reason they're not listing bit 6. I have no clue why. They say all of them are reserved. I'm going to assume this is the enable. So I searched the datasheet. I did not find any conclusive thing about this bit. This is I've literally no clue what this bit does, but we are actually not going to be using this register at all. Okay, then we have the auto trigger sources. We are not actually going to be using them, but this is all the type of sources you can use for ADC conversion. So you can use any of the timers to trigger an ADC conversion. You can use an external interrupt. You have an analog comparator, and then you have free running mode, which basically just runs a conversion as soon as the previous conversion is done, but we're not going to use this. And then we have the digital input disable register. This is the register we use to select if a pin is either an analog pin or a digital pin. Now note 7 and 6 have no value, and then if you go down to note, you'll see ADC pin 7 and 6 do not have digital input buffers and therefore are not required to digital input disable bits. These two are permanent analog pins, so you don't need to set up these pins. Now the one we are interested in is ADC 5D, which is bit 5 conveniently. You'll see the initial value of the register is completely 0, so all the pins that support analog functionality are by default digital inputs. When this bit is written 1, the digital input buffer on the corresponding ADC pin is disabled. And something of interest, the corresponding pin register bit will always read as 0 when this bit is set. So you will always get a logic 0 on this pin when you're in analog state. And that's our registers on the ATmega328P for the analog to digital converter. Let's get to the coding. So I have a basic setup here. I've already created .h and .c files for the ADC, which is this include. I'm including the UART. I have a print print buffer for the UART, which I'm basically just going to use to print out stuff. I made a constant char just to tell me when the program has started and just move on my clear buffer when I have putty open. Then we initialize the UART at baud rate 9600 in low speed mode. We enable here the 2 port pins as output for the lower half of the B port and the upper half of the D port. This is just so that we can output on the LEDs. We enable the interrupts as usual. Just after our initialization, we send over our start program string just to tell us, hey, I have booted, and then we set the port B equals to this run variable just to test the LEDs. You can set this to anything, it doesn't really matter. It's going to update so fast we won't even see it. Then we have our ADC.whole, which has some of our basic includes in it, and then an empty ADC whole.c file. So first we are going to start with a function, and we'll call it void ADC init, and we give it void parameters. The first register we are going to set in ADC init is our ADC mux register, and we are going to set that OR equals to 0B01. Now this selects our voltage reference, and then we just bit shift it by, then we go and look it up in our ADC mux registers R. We see we have ADC reference voltage select, which is bit 6, which is the lowest one. Then we just bit shift that in, and then we have our ADC and status control register 8. The first thing we want here is to enable the ADC, so we take the register, we put that OR equals to 1 left shifted by, you just find it here, our ADC enable bit. We OR that with 1 left shifted, and then we want our interrupt enable bit, which is ADIE, which we enable that one. We OR again, and then we want to select our prescaler, which is 111. So we say 0B111 left shifted by ADPS 0, so the lowest bit in the ADPS, so we can move all 3 those bits in one, and that is going to be our enable. Now what I'm going to do is just quickly going to add that function. So now we have a reference, now we can call this function, and now what I'm going to create is a enum, and this enumerator is going to be used to select any of the ADC channels. So we have ADC 0, so we have ADC underscore pin, so we have ADC 0, comma, and then we just create all the ADCs for us. So we have ADC 0, 1, 2, 3, 4, 5, and 6. Copy that. Just that, we create 7, then we have our last one, which is ADC 8, and that is going to be, remove that from the datasheet, that is going to be the temperature. Control Shift U to uppercase, and then we have 2 more inputs, which is going to be ADC 1V1, so the 1.1 volts, and then we're going to say ADC GND, and we are going to have to skip a few values, so that is going to be 0B1110. So basically we have equivalent value from all the way from 0 to 8, and then we skip a bunch of values to 14 all the way to 15. So now we have a numerator which we can use to select pins from, and we're going to create another function. We're going to call it void, and we're going to say it's ADC pin underscore enable, and we're passing in a uint 8, and we say pin. And then what that is going to do is we are going down to the dir 0 select, and we say OR equals 1 shifted by pin. We can enable any pin as analog input now. The next function we are going to create is ADC pin, and we say disable, and we say that is and equals to not the pin shifted value. So this disables an ADC pin and sets it back to digital pin. Another function we create is void ADC underscore pin underscore select, and that's again going to take in a uint 8 underscore t, and we say pin again. Now the pin selection is the very last pin, and it can only have one value. we take our ADC mux register, which we had in init. We set that and equals to 0xf0, so clear the lower 4 bits and leave the upper 4 bits alone. And then we have ADmux is or equals to pin, and actually I am going to change that to source for the ADC mux. Then we have our final function, which is going to be uint16 ADC underscore convert, and that is going to take in void parameters. Now we create 2 temporary variables in here, which is going to be ADCL. It's going to try to capitalize it. You don't want it to capitalize these 2 values. And then we have ADCH. Now these are just going to be temporary storage, and while we're at this function I need to create a global variable that is volatile static uint8, and that is going to be ADC underscore convert underscore done is equals to 1, because I forgot to create the interrupt function. So for interrupt we're going to say ISR, and we can look up the vector in our .h file. You can see ADC vect. So we just copy that name and plop that into our ISR macro, and we take our ADC convert. I need to correct that spelling, and we say that is equals to 0. So every time a conversion is done, it sets the ADC convert done to 0. So now we can go back to our ADC convert function, which I horribly spelled wrong. Okay, it's spelled correctly now. So we take our ADC convert done, we put that equals to 0. My interrupt is incorrect. I need to set that back to 1. So we set ADC convert equals to 0. And then we go to our status and control register A. We want to start a conversion. So we get our ADC register A. Copy that. We go to C. We say or equals 1 left shifted by the AD start conversion. So ADSC. So we start the ADC's conversion over here. And then we say while ADC convert done is equivalent to 0. We sit and wait here. And then we are going to see something that it looks wrong, but it's actually correct. We take our ADC convert register, Control Shift U, that uppercases it, so it gives us the register. Then we take our high dummy value and we say copy that, and then we also Control Shift U it for uppercase, and then we return ADCH left shifted by 8 and ORed with ADCL. Now someone will tell me in the comments, you can just put in these 2 registers right here. Guess what? Somehow in the optimization, it doesn't read the high register. And then you just continuously get the same value. It reads once and doesn't read ever again if you don't do this terribleness. Now we can quickly just add our functions to the header file. Now we have all our functions. Now we can go to the main loop. After our UART init, it actually doesn't matter as long as it's before the interrupt enable that you do this. You can init the ADC. Then we are going to enable our pin as an analog pin. So we call our enable function. We go to our header file. We want to use ADC pin 5. And we stick that into the enable, and then we want to select our ADC pin as the converter. So we take our ADC pin select, and then we can pass in ADC convert. And now just a reminder, this is because I did this enum that we can do this. Okay, so that is all we need to do to set up the ADC now. And now we can go to our infinite loop. But before we do that, before I forget, we declare a uint 16 underscore t, and we just call that convert and make that equals to 0. So this is going to store our conversion value. So we take ADC convert, we go to our main loop, we tab that in, we say that is equals to ADC convert. So that will pull the value for us, and then we can go to go to implementation for the .c file. I think I forgot to explain this. We have the ADC convert variable here, which is a global variable that just manages via the interrupt for us. So we set it to 0. We start the conversion. We wait while it is 0. And as soon as the interrupt triggers, it goes to 1. Then it breaks this loop. We read the registers and then we output the registers as a UN16 value. So we shift these up by 8 bits and or it with the ADCL low bits. So we produce a UN16 value on the side. Then I'm going to add something else to the header file, which is a conversion macro. Under our includes, we're going to do hash define ADC underscore volt, and that is going to take a parameter of x. And we are just going to take this, we're going to say x is multiplied by internal 5.0 divided by 1024.0. The 0.0 just makes sure the compiler knows it's a floating point number that we're converting. And this is just a macro so that we can convert to voltage. So we take ADC volt, we place that here, we take convert, we pass that in, and then we have a float, and that's equals to ADC volt. And we'll say volts for voltage conversion. And then we take our print buffer, we say mem set, we say print buffer, we say 0, we say size of print buffer. So basically this sets the entire print buffer to 0. And then we take, I have pre-prepared this, we have our print buffer, we say sprintf, print buffer ADC, this will give us the hexadecimal value, and this will give us the floating point value. And then we take a UART send string and we say just send the print buffer over. So this will print out the value now on the UART. And then we're going to use this run value I declared earlier. And we're going to set that equals to convert left shifted by 2. So this converts the 10-bit ADC value to an 8-bit ADC value. So you chop off the last 2 bits so that you can display it on an 8-bit port for the LEDs. I could have displayed the full 10-bit ADC port, but this is actually pretty common where you have to chop off ADC bits. And then I'm just going to copy this up here. So what we do here is we clear the upper 4 LEDs of port D, we clear the lower LEDs of port B, we set port D equals to the run, we filter out the lower 4 bits and we move them up by 4, so the upper half of the D port is set by whatever is in the lower half of run. Then we do the exact same for the B port, except we take the upper 4 bits of run and we set the upper 4 bits of run equal to the lower 4 bits of port B, and that will give us a nice linear display of the ADC on the LEDs. Okay, now let's program the ATmega328P. The build configuration, you want to go to toolchain, you want to go to the linker settings, you go to general, you want to say, you want to tick use a vprintf library, you want to have that enabled, and then in miscellaneous under the linker you also want to add dash printf underscore flt. So the dash is a linker option and it says printf support for floating numbers. Okay, now let's have a look at the demo. Now just something to note. You can see this white LED is kind of on, which is the most significant bit. You can actually see it through my nail that it is on. That is just the program header that is syncing current. So if I pull out the programming header, you can see it is off. You can see also no light out there. So we have 0 volt displayed on putty, and then you can also see when I turn the pot, you can see the voltage increase, and then also the LEDs running up and down. And now I'm going to switch off the light source. Okay, now I switched off the light source, and now we are going to see the LEDs go beautifully in color sequences. So as I increase the voltage, you'll see the LEDs rise up in a binary fashion, and then also you can see it on putty. And that's an introduction to using the ADC on an ATmega328P. The code will be on Git. Like, share, comment and subscribe is always appreciated. There are also some socials in the description. Thank you. Have a nice day. More disco, 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 disco.